making sure we're gonna move on and each stage of the project
Just a
you
minute.
are working on. That is the mostly what we supposed to complete for the rest of the semester. Okay, so we decide what topic you're gonna investigate, and then from there it is really the very much the first thing we need to do uh, from all the literature you've done. What is the most clear clean and also the straightforward and most concise statement what you want to measure for your research. Okay, so the next stage of the project is I want you guys really write up, okay, your hypothesis. Okay, with most of academic, which you read academic journal article as a graduate student, academic journal articles and the book, and they do not always have only one research questions or hypothesis. Rather than that, they have a set of hypotheses, uh, at least two or three. Okay, but most common numbers of the hypothesis in each test or each study is usually 4 to 5 or 6. Okay, but it's not very common that if you have more than 10 hypotheses to test. Okay, so the next stage we want to move on before we really just select the exact variable and clean the variable and run analysis. I want you guys to really write the clear, concise hypothesis, at least three hypotheses. When I say hypothesis as what we talked about a couple, 2, 3 weeks ago about hypothesis. So what is hypothesis? And there are two conditions and two requirements to be quantitative hypothesis test. First thing we already practiced, it should be theory driven. Okay, so it's supposed to not be nonsense kind of assumption. All right. So when you hear the hypothesis, oh yeah, it just makes sense. Why it makes sense? Because it is just driven by or based on pre-existing knowledge, fact, and understanding we have in our society. So when I say theory-driven, do not think too deep. It is something common sense we know by the theory, established knowledge, and numerous studies is already done in the field. Okay, and then the second one, and I think we talked about we don't test aliens, right? The reason is hypothesis test is about statistics. Okay, especially this course we are dealing with statistical analysis, dealing with the real world data set, mostly the second data set. So it should be tangible existing number, something you cannot measure in some way, somehow, then it is not something you can use as a hypothesis. All right. So just when you write up hypothesis, making sure it's a theory driven so it's understandable. It makes sense. It's not nonsense statement, okay? And then it is testable. So I already know what secondary data set you guys are gonna use. So I know it is already testable. We have a samples, we're subject, and there's numbers already measured, so it's testable. All right. So when you write up your hypothesis, you should be precise and concise. So I want you guys really look at. I know you already just went over the secondary data set, not completely, but you know what potential variables you're gonna use it for your study, right? Your project. So you might have the already specific variables or sets of variables or specific concept, theoretical concept, but it might be moderate, modified versions of a concept because you need to adjust, the availability. Okay. The second data set usually, not always, provide exact variable, the exact concept you want to measure, right? So just how you want to really make the statement with the most appropriate terminology, wording, and term, that's what you need to decide in this stage. Okay. And then what kind of factors, okay, in your hypothesis. So when you write up hypothesis, make sure it's not research question. It should be declarative sentences. All right. So A is happening, then B is more likely to be. Or, maybe when C condition is, satisfied, and D will occur, or D is more likely to be than E condition. So I want you guys to be very clear about what you are measuring rather than what's going to happen. And is that going to be uh, some, there's some significance? Is there any differences? Forget about I'm sorry, the research questions, right? And the declarative sentences. And then I know what kind of a relationship among the variables you wanna investigate and explore in your research, but just identify some sort of a relationship. It's causal relationship, positive relationship, negative relationship, or sometimes no relationship at all. Sometimes it could be important, hypothesis you wanted to test as well. Okay, so most of the hypothesis, it is usually between two, three, four different variables, and what are the relationship among those variables? That's the most common hypothesis we test in statistics, and if you can be specific as much as you can. Okay, so that actually leads you much easier transition from the hypothesis session to actual, the data cleaning session. Okay, so when you're specific, okay, what you want to say about the A happen, okay, so A will be this variable, so it will make it a smooth transition. So if you have a very specific uh, declarative relationship in your hypothesis, it's a beautiful part. Okay, so that is actually due Tuesday next week. Okay, if you have a five, six, seven hypothesis, that's totally fine. And if you wanted to have just at least two, three hypotheses, that's totally good. Okay, but I know based on the number of variables you want to test, make sure once you run any types of any method of statistics, at the end of the hypothesis testing, you can say this hypothesis was confirmed, or this statistical analysis proved the hypothesis, or this hypothesis was not able to be confirmed. So that's the sum of, the conclusion you should write up, and whether it's statistically significant or not, right? Do not really merge two different hypotheses into one. Sometimes you can do that in real world research, but the purpose of this project is that when you have a hypothesis, you run appropriate the statistical test, and if at the end you can write up the result for each hypothesis. So it will make easier for you to have a very specific hypothesis that can be confirmed or not confirmed by one or two hypothesis testing. So in other words, using one or two statistical analysis, you should be able to say, yes, it is statistically significant. No, it is insignificant. All right. But if you have a multiple questions, multiple hypotheses in one hypothesis, it's hard to confirm. Yeah, it's a partially, but in this case, it makes much more cumbersome to move it through each stage. Okay. So clear and one hypothesis at a time. Okay, and it's more of just arbitrary thing that I say two to three, but the number of hypotheses in this stage is not part of grade. Okay, just a write up, um, good, clear, declarative, and specific hypothesis. Any question about what you needed to do? So it's clear. Okay. All right. So if you start right now, this is today, and if you have any question, and also a couple of hypotheses you want to bring to the class, uh, following to in the Thursday class, and I will see, okay, this is a great hypothesis, or what about if we modify the hypothesis in that way? Is there any other way we can specify better? So we can talk about that. So if you bring a couple of hypotheses for the beginning of I'm sorry, Thursday class, we'll talk about it before you submit the hypothesis on Tuesday next week. Okay. All right. So let me stop sharing our Canvas course site, and then let me share class note. All right. Okay, so we just talked about the next stage of the project. Okay, so good luck and have fun. All right, so starting from now we completed our exam, and by the end of the actual the lectures and discussion, if you remember, I'm sure you study and you've done exam well. We talked about t-test family. Okay, so we talked about t-test family is the purpose of statistical analysis, especially when we are comparing two different things. So two different groups or two different conditions in time or context for the same people. So whatever we compare between two things or conditions or anything related to groups, uh, that is a t-test family. So the basic form of the t-test, we compare how my samples are different from the population. It's a t-test, basic t-test. If there's a two groups, male and female, we compare two groups, the independent sample of the t-test. If you want to compare some of the changes over time, before election, after election, or before exposure to some of the like experimental stimuli, and after. So you compare pre-post, that was a repeated measure to t-test. Now, this week, we're gonna move on thinking about real world research question. We have multiple groups to compare, right? Multiple levels of conditions and changes over time. So even thinking about different ethnicity group in American society, how their political or social connection or identity, it's gonna, you know, affect political decision, right? In that case, you are beyond the conditions of the t-test. You are comparing more than two groups, two conditions. Then you should move with Anova test. So this week, especially next 2 weeks, we're gonna talk about the Anova test family. Okay, so Anova is an analysis of variance. Okay, so variance. Oh, I know what is a variance. We talked about variance as a step before standard deviation, right? Just measuring the variability. So variability means how widely and varied those differences between people and among the people. That's it's just a numeric concept, the numeric measures we use for ANOVA tests. So it's compared to how we call and the name and the distribution, the alpha distribution, it's much simpler concept, maybe much simpler than even t-test. But as I mentioned that the statistical foundation, the formula stay the same. All right. So what they're measuring between the groups and between conditions, that's what we're gonna look at, and then we just see what kind of errors and variabilities, okay, by chance it's gonna affect those differences. So that's what we're gonna look at. So let's move on. So as I mentioned that t-test and alpha test, they are both the test for comparing different groups. Right. So as I mentioned, the t-test look at the differences between two groups and two conditions, right? And the distance between two groups, for example, and then What about over the variability as at the bottom as error? Okay, and then the two condition, then the differences or changes between two conditions, that's a numerator, and then the variability between two conditions and changes over two conditions, that's a new denominator. So that's the structures of the t-test. And then having that, just let's think about the actual example. Okay, so this is not like a pre-post test, but some of the questions, for example, there are a variety of different pedagogical educational method. Okay, so that is what most of the educators and scholars in education, they try to test what method should work best. So, for example, in order to teach a statistic course, okay, intro to intermediate to advanced, and what is gonna work best? So mainly it's a theory oriented, so just learning basically what we have done so far. Okay, 2/3 of our lecture is all theory. Okay, 1/3 of the lecture and every part of the Thursday class, we really practice and run some analysis with the market available statistical software, right? That's what how I design it. But some some courses, they are purely all theoretical, and so they use a textbook. They never really talk about or practice SPSS. But nowadays, I just see many intro level of statistics. They just simply learn. Um, the statistical applications utilizing different statistical software. Okay, so I don't know which way is a better way to teach statistics. Okay, but over 20 years of my teaching experience with the statistics course, I thought once you learn theory and then practically how to really just use a secondary data set, run numbers, and then know how to interpret it. It's like a linear. That's how you can complete or understand some of academic work out there. That's what I thought it's just the best way. But not all statisticians and the faculty or teachers in who teaching statistics agree with me. So I wanted to test uh, 4, 5, or 6 different statistical teaching pedagogical method proportion wise. Is that all weekly quiz versus, for example, our course, weekly quiz as a practice, and then midterm exam and project. I just combine all of them just to see how you can learn in different way. So what might be the best way to learn? Okay. So if it is the research question, if it is the hypothesis, I believe my uh just the design of the course might gonna maximize the student learning as the intro and intermediate level of statistics course. So in order to test it, I want to say, okay, mine as the group one and method one, and only statistical theories, and group two, only practical statistical analysis with the software, group three, and maybe only, some hybrid, 30%, 50%, or 80%. So all variety of them. So let's say we have 6 different kinds of or method or approaches teaching statistical course for this level. So what we needed to do based on what we know so far is, okay, we already know you can compare group one in the method one teaching method one to teaching method two, or one to two, one to three, four, and so you can do all pairwise comparison. You can do that through independent sample to t-test, don't you? Right? So, but think about it. How tedious it will be going over each pairwise, okay, comparison. And then eventually you see, okay, uh, the method one is better than method three. but method 6 is better than method 3. So, and then I need to test the one, method 1 and method 6. And so it's all confusing if your research question is not measuring all areas and all like those pairwise comparison. If your research question is actually if there's any teaching method and approach is better than another, then maybe we should use one over the other. So your research question is not to test all pairwise comparison, but any teaching method should work better than another. Okay, so you want to test all these methods all together. Not all the teaching methods are the same. There's a way better way to teach a statistical course. So you want to test all these areas, all those pairwise comparison, all at the same time, and find and detect any evidence that one or two and multiple method had a more effective learning based on the student's performance, depending on the dependent variables anyway. So when you want to test all these multi-group comparison all at the same time, that is Anova test. Okay, so that means more than two groups, but all these pairwise comparison all at the same time and see if there's any evidence that one or two or multiple groups are different from each other. So we called and named this statistics is as ANOVA. This is most the statistical term called when you compare multiple groups, analysis of a variance. Okay, most common name of this analysis. Okay, but some statistical textbook and some statisticians, they actually called ANOVA test as a F test. Why? Because now for ANOVA test, we use F distribution table. Okay, so they are different from Z table and T table, what we covered, and I will show you in a minute how they look like. And also, some statistical textbook, especially those statistical textbook in a statistics department, they use more of the statistics oriented rather than less applications. Again, different method. But they use term F ratio test in place of ANOVA, but it's same test. Why they say F ratio? Because in terms of those statistical formula and structure, they compare the variance between different groups, okay, and the ratio of the variance across all the group and across everybody. Okay, so that's how they put their statistical approaches in the formula into the as a what we know as a foundational statistical structure, right? What we are comparing as a numerator, as any error term as a denominator. So they compare the ratio between numerator and denominator. So they statisticians they are comfortable to call ANOVA test as F ratio test. Okay, great. So let's just start with ANOVA test. The purpose of ANOVA test is to test multiple groups differences using F distribution table. Okay. So when you have one variable, but within one variable there are multiple um, groups in one variable. So like partisan group, like a Republican, Democrat, and Independent. It's multiple group, but it is a pi ID. Okay, it's what we call that is a one factor or one way ANOVA test. Right? And it will be the discussion for next week. But you have some kind of comparison across different groups, right? What about, find the national um, public opinion surveys for, several, the decades. And American voters, political view, especially when the multiple factors are combined, like when we compare, okay, Republican, they are more likely to be conservative, okay. But when we combine, for example, gender, okay, female Republicans are most conservative, okay. So that is actually the national value we found for multiple decades, okay. So when you combine two factors together, like gender and party ID, then it is a two-way or multi-factor ANOVA test. If you combine three factors, ethnicity, party ID, and gender, it's a three-way and three-factor ANOVA test. Okay, so that's how you call one-way ANOVA, two-way ANOVA, three-way ANOVA. So we're gonna talk about one-way ANOVA this week. And next week, we're going to talk about multi-factor, two-way, three-way ANOVA test, as well as repeated measures ANOVA. That is the next week's topic. So we compare different groups. It's one under one variable, but there, uh, just in order to understand, the structure of statistics, I want to make sure we are on the same page, okay, about the notation. And some of those statistical notation, it's universal, it's identical across the different textbook. But like here, when I say uh, G or K, it is used as a notation for the number of groups, okay? Numbers of groups. If you see G or K in academic journal article, you automatically just should know, okay, it is not like the sum of correlations, relations, regressions. It is actually comparison between different groups. Okay, so whenever you see G or K, that's the number of groups you are comparing. It's important notations you wanted to know for the comparison group. So ANOVA test, you write up your hypothesis in a little bit unique way. All right. So null hypothesis means we want to falsify. We want to find evidence all the groups in our variable in the sample. They're all the same. That's what we want to falsify. So if it is so falsified, and I'm sure you know how the logic works, if null hypothesis is rejected, alternatively, we argue that our alternative hypothesis are accepted. Okay, so that is the way we can make statistical decision. So null hypothesis for ANOVA test, all groups. If there's three groups, group one is equal to group two, group two is equal to group three, and all of them are three. So that's the notation you can use. Okay? Or you can simply state in plain English in full sentence. All group means are the same. All the proportions across the different groups in the sample, they are the same. So you can use the plain full sentences. Okay. And then when you talk about alternative hypothesis, okay, and let me come back to this slide. If I look at this circumstance, okay, and depending on your hypothesis, you want to specifically confirm method A is different from method 3. Or you want your hypothesis, all three teaching methods or all six teaching methods should be all different. Or at least one of those, teaching method should make a difference. Not all the teaching style or teaching method or pedagogy are the same result, right? So if that is your research question, unless you want to specifically identify any of the specific difference in a pair, you can write a general, broader alternative hypothesis you're testing with Anova test. So here, when you see here I or J, that's the random group, random case in statistical notation. So when I and J is not the same group, okay, they are not the same group, and at least one random group is different from another random group. So if we write in plain English, we can say at least one population group and their mean or their whatever you're measuring, um, the value is different from another. That's how you can write up in order to cover all the possibilities of the hypothesis and significance. Okay, so that's what you do for ANOVA test. Okay, any questions so far in terms of hypothesis? Okay, good. So here, there is also assumptions and requirements we need to understand. Again, when we talk about t-test, we assume that, yeah, dependent variables should be normally distributed. So we can use the normal and t-distribution that is normally mostly like look like symmetrical. So there are some of the common knowledge and common sense whether I can test this with this specific statistics. Same thing for ANOVA, and as I emphasized that you don't need to memorize, okay? You don't need to prove it, but the required assumptions in order to run ANOVA test, we wanted to make it sure. Okay, so for example, group one and group two and group three. Okay, they represent, okay, a random sample for the group. So when we compare Republicans versus Democrats versus independents, and for Republicans among that group, they are independent each other. You do not want it to, in American politics. It's getting less, and some of your political location, sometimes the tendency is stronger, but parents, children, political affiliations, and party affiliations are very much highly identical. Okay, so for that reason, when we compare different group, each group they should be random, independent samples. They are not related to each other. Okay, and also each group, whatever you are testing for their dependent variable, so each group on their dependent variable, they are normally distributed. Okay, so they're still the final dependent variable for each group. It is normally distributed. Okay, they are so when we have, for example, oh, let's really see. Let's say group one. It is normally distributed for the mean comparison test. If you pick one mean and out of the normally distributed distribution, mean is the most representative value, right? But let's say a group B somehow ended up with really, barely negatively skewed. Okay, then you just pick a variable. I mean, I'm sorry, mean value out of the group B that is negatively skewed. The mean value is not the best value to plot to compare to other groups because it's skewed and the mean values out of skewed distribution, it's a not representative value. So from group A, it's a most representative value because it's normally distributed. Well, group B, it is a skewed variable, so mean value is not best representative. It is more likely to be biased by extreme score. It's not a good comparison. Okay, that's the reason we don't want to just we want to at least assume that dependent variable for each groups they are normally distributed. So the value we compare, that's most representative value. Okay, so that's assumption. And also, the last required assumption is across a different group, they have a similar, same thing as independent sample to t-test we talked about. They have a similar variability. Do you remember when I talked about, okay, some example, it's doable and not doable. It's legitimate or not legitimate. So when we compare, for example, compare Texans with the Floridian, totally fine, right? But when I compare that legitimate question, I ask you guys, what about if we compare Texans with the Chinese? It's not gonna work, and your brain kind of stop moment. Why? It sounds weird. Why Texans and particularly specific state in United States with the one huge territorial wise, but much different political system. Why? That's the question because the very theoretically and the knowledge we already have, we know that if different group had a different variability. Theoretically, it's not gonna be comparable. We cannot really compare them legitimately, right? So that's the reason. So the third requirement for the Anova test, like a t-test, okay, independent sample to t-test, the variability across group A and group B and group C and D and F, um, they all have a similar variability for denominator. So it's a legitimate, and those statistical analysis, it's not going to violate um, the numerical values. Okay? So that's required assumptions. Again, do not memorize. It's a common sense. Oh, so normally distributed, dependent variables or whatever we pulled out, that's good numbers, good representative number to compare. And then we wanted to make sure the variabilities, they are similar across the different group. So when we compare values. Okay? So that's a required assumptions. Again, do not memorize. It's a common sense. Oh, so normally distributed, dependent variables or whatever we pulled out, that's good numbers, good representative number to compare. And then we wanted to make sure the variabilities, they are similar across the different group. So when we compare it, not gonna be too biased. And also each group should represent the population. Okay, not correlated too much among themselves, or not correlated to from the group to group B and group C, and it's gonna violate ANOVA test assumption. Then the result might ended up with not very reliable, not much, value. So you should think about that foundations and assumptions to test it. Okay. So it might be easiest way for you to understand the move from t-test to ANOVA. So same thing. All right. We are still comparing group. But t-test, we are comparing different group, but especially between only two group. And ANOVA test multiple group. But do not forget, still your independent variable is categorical group variable, and your dependent variable is something numeric, so we can compare mean values or proportions and any variability depending on your hypothesis. We're comparing something about each group. Okay, so that is the differences between ANOVA and t-test. So let's see where we are in statistical roadmap. Okay, so last week before the exam, we were here. We have a categorical group variable, and then we're comparing something among those group for the numeric and interval dependent variable when the group had only two different dichotomous, you know, categories: male, female, pre and post. But what about if we have multiple groups more than at least three and more? Then we are still here under a variable, categorical, nominal, independent variable. That is what we're comparing. And then dependent variables should be something numeric, so we kind of quantify the information about each group and compare. So we are still one nominal independent variable and one interval dependent variable. And then, but the condition wise, we have three and more categories and groups to compare. So that will be this week. And then next week, we're gonna move on with multiple levels and multiple groups, even interaction. And what about the same group, but multiple conditions and situations, and then different point in time, but it is more than three different conditions and three different time, then it's not repeated as repeated measures at t-test, then it is a repeated measures ANOVA. So anything between two, it's a t-test family. Anything more than two, it's an ANOVA test family. Okay? So for the t-test, um, especially independent sample to t-test, that's what I'm comparing right now. We looked at, okay, group A and group B. That's the numerator. And denominator is, okay, what is all the error from group A and B combined, right? So that then the statistic value of T has a strong and high value, that means it's strong. There's larger differences between group A and group B, in group A and B, and one or two. So that means we can say it is statistically significant, right? So we're gonna stay the same statistical foundation and formula. Okay. But the concept wise, it might be easier with a little bit of a modification. So it's not anymore between two groups, but it's among the groups, right? Among the groups, if those are the differences among the total, pairwise comparison and all that, if it is different in anywhere, if we detect that, it is statistically significant. That's ANOVA test. So instead of between group, we say variance between groups. Instead of a between group, difference between groups, it is a variance between groups because it's multiple. Okay. And also not between across the two groups, it's a variance across all different conditions and groups more than two. So what ANOVA tests they are doing numerically and statistically, they are comparing any of those variability across different groups compared to any of the variability by chance that occur within group and across the group together. Okay, but the same concept, Anything we compare between groups should be numerator. Anything we're comparing across or among the groups should be the denominator as error term. So as I'm not lying it, right? The foundations of statistics stay the same. Okay. Maybe a little bit of terminology differences. So I want you guys to understand it. So across different textbook, when we say within group variance, within group estimate, that's a denominator. But some textbook really stayed out as that is a variability of, the statistically it's a variability in each group. Okay, there are like when we have a representative group for each population group, different population group or whatever you have as your comparison group. There are some nobody knows, there's no two say, same identical pair. We are people, we're all different. There are just some variations across the different, people in a group and within group. So variability within each sample, variance within the treatment and the tendencies, or the time, different point in time, or just simply error. That's within group estimate, within group variances. Right? When I say between group estimator, estimation, that's what we do exactly your hypothesis and my hypothesis try to test. So Republican is different from Democrat, or Democrat is different from independent. Let's make sure there are some group differences, okay, beyond any error by chance, which is what we're going to put as the numeric values as a denominator. I'm sorry. Yes, denominators. Okay, numerator. That's what you are testing. What you want to see as the changes and differences. Within group estimators, that goes to um, denominator. Okay, just control those error. So as I mentioned that earlier, statisticians, they would like to call Anova test as F-ratio test. Why? Eventually what we do for Anova test, we're comparing the differences between group, so variance between group compared to all the variance differences across any individuals in the group and within the, across the group. And also we compare any error by chance. That's something we have as a baseline and numerator. Then the differences across the different groups, that's distinctive enough and larger enough. So if it is a larger enough and more than just a random chance error, why they are different, then it is statistically significant. So ANOVA test compare the ratio of variance between group and within group. That's it. Okay, so that is why statisticians they like to call ANOVA test as F ratio test. So let's use actual example and see how the numbers are turned out. So rather than I just try to explain conceptually how it's gonna work, but you can actually plug in the numbers and see how the formula works and just see how those statistical foundation and structures they stay the same. Right? Um, in American politics, political ideology and political party affiliation, is that the same thing? What do you think? In American politics in 2024 and 2025, political ID is the same thing as ideology. What do you think? Let's have a little bit of a discussion here. It might be relevant to some of your, possibly some of your selections of your um, variables for your project. In American politics, political ideology and political party affiliation, is that the same thing?
No.
No. Why?
Um, I think I mean, someone who is like, say, extremely, um, like, uh, moderate might vote either way. Like they
Sure.
might vote left or right.
Mhm. That's true. It, maybe statistically, maybe more Republicans tend to be ideologically, conservative. Vice versa, there's some sort of relationships going on. But as you what you said, as independent, you're independent in terms of in, belong to neither party, but you always so being so conservative, right? That could happen. It depends on the ANS data set. Okay, so you know how long that data set had been. So when we look at political ideology and political party affiliations, between 20 and 30% of the sample that are most representative, they are not really aligned with partisanship with the political ideology. There's a one fun statement by a political psychologist. His name is Weston, Drew Weston. Okay. He said that Americans, Americans' political party affiliation is sometimes totally irrelevant, and also, our political attitude is pretty much very ambivalent. So, what he was arguing is through the testing and utilizing ANS data set and GSS data set, he actually confirmed that uh, American voters, we are very much leaning to, okay, conservative side, okay, not like extreme, but more likely to be conservative than liberal in political ideology. But when he went into the specific questions, policy directions, and policy issues, actually American voters are more likely to leaning to liberal policy in operational wise, practical and operational policy wise. So that's what it really, just to give you some idea, right? Political party identification and ideology, it's not always straightforward. It's always a clear cut kind of relationship. So although it's related, partisanship and political ideologies are not identical things in American politics. So let's measure here three different partisan groups and how their political ideology vary. Okay, so for example, Democrats usually they're more leaning to liberal side. However, their ideologies and their ideological spectrums are much broadly spread out because you know um, in American politics over the last 40 years, 50 years. And we tend to have a broader demographic groups as a Democrat. And Republicans tend to be more, cohesive political, social, and socioeconomic groups, right, compared to Democrat and something like that. So just ideology, that is how varied they are, okay? In terms of narrow and wider and something like that. But there are as American voters, and this is across the different partisanship, and we want to compare that theoretically doable. So our null hypothesis we want to falsify is wanted to falsify is well, Democrat and Independent and Republican, they are all same in their political ideology. Yeah? Um, so that we wanted to disprove, so we can prove that our alternative hypothesis, yeah, American political party affiliated voters, they have all different ideology. Okay, that's what we want to prove. So here there is two things and two notations. Again, to be honest with you, What I'm gonna cover for next 5 to 7 minutes, you don't need it to do on your own. Okay, from now with the complexity in the calculation, also the sample size we use, we are not gonna do any mental math or hand calculation anymore. We will let the software deal with it. But still, my role is I want you guys understand how what the statistics software what they're doing for us. Okay, when they kind of showed the finer test table with the finer value of the alpha value and p value, where this number coming from. So at least I need to explain. But as long as you understand logic, don't worry about, you don't need to memorize, you don't need to calculate anymore. Well, let me go over it for you. Okay. Um, so as except as what we talk about z normal distribution, anything from p table and rest of the distribution table we're dealing with in statistical conventional and traditional statistics. We have a statistical distribution that are established and accumulated by multiple experiments. So Anova test we use F distribution table. Okay, so if set the Z P table, now F table, we still need to know degrees of freedom. So how many values are in the sample we fixed, so except that particular value, rest of the value can be anything and any value. That is degrees of freedom, but it goes with the sample size, right? Simply, uh, the sample size -1, sample size -2, 2, 3, not no more than like a sample size -10. Okay, in market traditional statistical statistical analysis, but they are here in alpha test. We need to know statistically in order to read the alpha distribution table. We need to know two degrees of freedom. One is for between group degrees of freedom. Another one for denominator for within group degrees of freedom. Okay. So when we compare for between group for the theoretical, structure wise, or numerator, so between Republican, Democrat, and Independent. Okay. So in order to compare those three groups, so what we're gonna fix is that we fix all like just all mean, basically the mean for across all the group. So we call that as a grand mean to compare to Democrat, compared to Republican, and to compare to Independent. So when we have the degrees of freedom with between group, the group number again you can use a K or G -1 because we fix one grand mean for all group. So that is a degrees of freedom for between group variance. And then within group, we have a three group, Republicans, Democrats, and Independent. In order to compare, for example, Republicans, we fix a one mean among Republicans and compare all those variability within the Republicans, and we fixed another group mean for Democrat, another group mean for Independent, in order to calculate their own variabilities within each group and combine them all together. That is within within group variance. So degrees of freedom for within group degrees of freedom is a total sample size minus group each group mean. Now we fixed three for each group, Republican, Democrat, Independent. So that's how you need to do. You need to know. Now, okay, just I use some of the notations, but just to know what we are doing. Okay, you don't need to memorize. You don't need to do anything, but just let me explain it. If you get it and you understand the what they're operating in SPSS, it will be much easier for you to really interpret it later as well. So when I say within group variance, what they compare, okay, so you don't get upset about it. So each case, and then let's say it's a Republican variability. So each of the Republican in the sample compared to Republican mean, so summation of all of them. And each of the Democrat and Democrat grand mean and summation all of that. And each of the independent case and they compare to that independent groups mean and a summation of all of it. What is that? It's variance. Remember variance. It's a summation of the deviations, right? That was the variance. But in order to have a variance, what you need is divided by sample size minus one. That was what the basic form. Okay. But here we need to divide it by the degrees of freedom. That's denominators of Anova test. Okay. So within group, sum of squared of within group variance. Okay, and then sample size minus total group, since we fix each group mean to compare. Okay, calculate the variability for each group. That's denominator. Okay, and then between group variance, that's a numerator. Okay, the numerator, how you can calculate that? The mean value for Republican to grand mean for everybody. Okay, and the mean value for Democrat and compared to the mean grand mean and independent grand mean. So it is a between group. So here is a grand mean and between Republican, Democrat, and independent. That's a numerator, the value, but still it should be variance divided by sample size originally. But here is a variable. I'm sorry, the variance for between group. So we know we fix one grand mean. So it's a group number minus one. That's the degrees of freedom for between group. Okay. So this is a theory, and I want you guys to really see what's going on in statistical analysis and a statistical software, what they are doing behind the scene. All right. So if we plug in the total mean here, grand mean, and here with Democrat mean and independent mean, and then Republican mean, and all the sample size. Okay, and then the degrees of freedom divided by that, that is a degree, I'm sorry, it is a between group variance. This is the value we plug in into numerator of Anova test. This is a proportion of variability. We want to compare these group differences. It's a distinctive enough compared to what? Any error by chance, which what you're gonna compare. I will come back to this within group. Okay, so if we compare, just put the within group variance, that's it's gonna be denominator. Okay, so basically what I have done, compare between group and divided by degrees of freedom is gonna be mean, variance, and then the within, just across all those the groups, and this is a squared. Very square the summation of the square the deviations divided by degrees of freedom. That's a variance. So F test is the mean variance of the between group divided by mean variance for within group. That's the F test value. So 42 divided by 1.67, that's F value. That is the P value. Okay, so that is the theory. Okay, if you plug in the value, we got the alpha value of 25.6. Okay, so is that large value or small value? That's what we need to we have the hypothesis, we done hypothesis test. Now let's make a decision whether it's statistically significant or not. So we know how to read F distribution better. Okay, so F distribution can be negative value. You let me know. Negative, F distribution have ever have a negative value? Answer is no. Why? We use a squared value, any squared value for numerator and denominator. It makes a negative value to positive value, right? Whatever the variances are, we square the value, that's a positive value. So all alpha values are going to be all positive, okay? It's going to be all positive value. It's a ratio. But the by null hypothesis, if the ratio between group, ratio between within group, they are similar. If our null hypothesis is correct, it's gonna be the value closer to one, right? The ratio is one, then it's gonna be one. So after distribution, it is clustered up near one. That's how F distribution look like. And the F distribution was it is listed from the page, our textbook, main textbook theory book, from page 653 to 655. Okay, so let me show you how it looks like. Okay, F distribution all positive. Okay, and if it is very small size, it's just sort of a negative curve, but it's all positive values still. But as you see, you increase sample size, what's going to happen is that slowly, slowly, slowly convert to something not exactly normal distribution, but it's a somewhat like this, and some are more likely to spread closer to clustered up near one, but it's comparing to somewhat similar to closer to normal distribution as the sample size grows up and increase. Okay, so that's how F distribution look like. All right, so theoretically makes sense, right? And then this is actually how F distribution look like. Hmm. So F distribution is totally determined by the sample size. Again, these numbers are really established by statisticians, by numerous statistical context and the sample size and data. This is the accumulated values they come up with. Okay, but in order for us to use F distribution again, I do not expect you read the distribution table anymore. Okay, just so we're gonna rely on statistics software in our class as SPSS, they know this route. They have this information there. They produce those information out of the sample statistics, and they will let us know whether it is statistically compared based on the distribution table. So what we needed to know, but if we still wanted to visit after distribution. So this is a degrees of freedom for numerator. The numerator means you have the number of the groups. It's usually no more than 6, 5, 10. Usually 3 group comparison, 4 group comparison. So this is the numbers of the group, but you always fix one random mean out of all group. So if your degrees of freedom is 2, the actual group you're comparing is going to be actually 3. If your degrees of freedom is 3, actual groups you're comparing is actually 4. Okay, so this is degrees of freedom value. You just keep going down, and then each row represent what is the degrees of freedom for numerator. If your sample size is huge, like what we use for um, AS data set and GSS data set, as you see it on the page in the hard copy, degrees of freedom after distribution goes up to 1,000. Okay? But there's a random like interval from 65 to 70 and 100 and 125. So just as it gets larger, the incremental changes between the degrees of freedom, especially for numerator, I mean denominator, it's not a big deal. Not much changes. Okay, so here that's how you're gonna read it. But for each intersection of the numerator degrees of freedom and denominator's degrees of freedom, there's a two number. One, the light font, that is the fine line at the alpha value of zero point 0.5. What is the corresponding alpha value? The bold font, one below, is what is the corresponding finding alpha value at the alpha value and the critical value of 0.01. So when you're more rigorous and about the statistical testing, so that is a fine line of that the value. So in other words, it's alpha distribution in your statistical analysis out of a sample, your values are located in the critical region here in the blue section. Then it is statistically significant. So you want to see the borderline alpha value is 3.888, okay? But if your statistical value is larger than that, oh, okay, that means your p-value is smaller than that, right? As the statistical value gets larger, your probability for the null hypothesis gets smaller, right? That's how statistical logic works and how they design it. So you want to see your statistical value is larger than 388, then it is statistically significant. If you want to be more rigorous and more strict, okay, not able to make any type one error, okay, then you have the statistic value bigger than 7, closer to 7, then you can confirm your alternative hypothesis and reject the null hypothesis. Okay, so that's how alpha distribution look like and how to read alpha distribution. But again, I will I do not expect you really plug in numbers and calculate statistics as well as how to read the alpha distribution table. Okay. And I will go over what numbers you're gonna use for your report. And then after that, and I may stop there. And then starting Thursday class, I will go over one additional test. Okay, following test and post that test after F test. And then we're gonna practice with SPSS. But anyway, once you had a statistical analysis and variety of the statistics software will provide you alpha value and p value, okay, and so, but there, in order to read mostly the statistical distribution, especially T and F distribution table, the important values to read is degrees of freedom. So I recommend you, and statisticians, so they prefer to see the degrees of freedom before the statistic value. It's a small sample, larger sample, how many, the groups you are comparing, so within round bracket or a square bracket, depending on style, put the degrees of freedom. Group, between group, degrees of freedom first with a comma and degrees of freedom for denominator second, and then alpha value, and then p-value is smaller than zero point zero 0.01 or zero point zero 0.05. And then you will say, according to Anova test, especially now what we have done, according to one-way Anova test, we have the alpha value of 25 some point. That's a huge number. So we confirm that Republicans, Democrat, and Independents, they are not the same in their political ideology. At least one group is different from another. We confirm with the one-way ANOVA. Okay, so that's how you can write up your statistical result in writing. Okay, so but my last question for you to go with. Okay, so at least out of Innovatest, out of one way Innovatest, one factor Innovatest we just covered. The Innova test confirmed that at least one group is different from another, right? But we do not know how Republicans is different from Democrat is statistically significant, or how independent is different from Democrat, whether it is statistically significant. So once Innova test is statistically significant, we wanted to confirm which group from which. That's post-hoc test. That's automatically following up the test after ANOVA test. That's what it called, and it's a post-hoc test. It's just I want to introduce what tests name and what tests are more appropriate in terms of the, you know, uh, uh, you know, just after Anova test, what following up post postdoc test is appropriate. Okay, and how you actually calculate and theoretical understanding of it, it's not really relevant to our parameters of the statistical understanding. It's more of a multivariate and how you're gonna control those deplete or inflate variability tests. So we are not gonna cover that all, the different statistical approaches across different postdoc tests. But I will introduce what are the tests that we're gonna just look at. And then we're gonna move on to SPSS. Okay, so I will stop here. Up to this point, and we're gonna cover first 10 minutes for postdoc test and the rest of a class on Thursday. We will actually run a 1A ANOVA with this real world data set. Okay. All right. So I will stop here today. Any question about one-way ANOVA test? Okay. Otherwise, have a great afternoon and I will see you on Thursday. And again, if you can, couple of hypotheses, so bring the class so we can discuss it's good or not before you submit it on Tuesday class. Okay? All right. Have a great afternoon. I will see you on Thursday.
Thank you.
Thank you, ma'am.
Thank you.
Our university